Next class is fluid rheology. So it is related with fluid dynamics of physics, and this is more applicable in the industry also. And this one is slightly difficult to understand, but it is very easy. The topic is actually very easy, and I asked the students to go through this chapter, and it is very important and applicable in the industry as well. So the rheological properties of liquid is explained in this video. Just you can have a look. There are two liquids are poured in a vessel, and one is blue color and another one is orange color. You can see the blue color is flowing very fast, and the orange color is maybe it's more viscous, and the flow is very slow. So this is the best example for the rheological properties. And the first fluid is there is no resistance with the liquid. It is easily pourable. And the second one is the particle, the interaction is more, that is why it is resisting to flow. The fluid may have described in two different aspects. That is the Newtonian fluid and non-Newtonian fluid, depending on the flow characteristics of Newton's law of viscous flow, and that is a very important the physical parameter. I hope you already studied in your plus 2 level, and that is comes under the chapter fluidics. So this is the best example. Just maybe this can be explained in a model diagram. This is the diagram you can see here, and this is the boundary plate. That means just imagine there is a tube, and within the tube you are going to flow the fluid. This is just a boundary, the bottom boundary and the top boundary. Usually the top boundary is still more there, and this is the boundary of the liquid, that is a moving boundary, and this is a stationary boundary. That means this is a solid boundary, and you are pouring the liquid. So what will happen if the liquid flows? And you can see here in the starting from the bottom. So this is the glass, for example, is a glass or plastic or the water maybe. It is like a water tube. You are pouring the water tube to the garden, or something, and you can see the bottom side. That is coming. I'll show in the different diagram also. I'll use my pen to draw that. So this is a pipe. You are pouring the water, and the water is maybe coming in this direction. You can see here this the flow is a little fast on the top, and in the bottom the flow is less. Why? Means there is a friction here. So this layer will form a friction, and the top layer, that means the top layer means that is not touching that layer, and automatically if it is a half layer means the fluid will flow very fastly. I'll close that one. Again I am drawing another one. So this is, you can see it is a bigger one. So this is a pipe, and you are pouring the liquid. I will choose another color for that, maybe the green color for the liquid, and this is the liquid, the pouring out, and the bottom layer of the liquid is coming. You can see here the topmost layer. This is this layer. Actually this layer is the topmost layer, and the bottom layer is this one. That means, so this is the bottom layer. I hope you can understand this one now. And the top boundary layer is the moving layer. This one, the single tick is the moving layer, and the double tick is the static layer. You can see here this will create lot of friction. And this friction is maybe leaving the liquid to flow on the top more fast, and the bottom maybe less flow. So that is why the tube maybe giving the flow maybe very easily to the down, and also this is going little extra because there is no friction. So it is called as a shear stress. A stress is applied to the layers, between the layers. You can see here this is central layer is maybe the starting more shear, and the bottom lot of resistance will be there. So this gradient is called as du by dy, that is dou u by dou y. And this is the speed of the liquid is called as velocity u, and shear stress is called as the tau, and the moving boundary, this is moving boundary, the topmost is the moving boundary, and the static boundary is the bottom one. So that is why the static boundary is always there, that is very slowly it will move. So that is why that will be falling in a very short distance. But the top one, if there is no resistance, if it is not touching this layer, automatically this will be moving very fast. So this is the best example for understanding of the fluid dynamics and fluidics. I hope you can understand this one. And the consider a fluid containing between the two parallel plates. There is a tube containing the top one and the bottom one, and this is the distance is x apart. If the lower plate is moving in one direction at the constant velocity, the fluid adjacent to the moving plate will move in the same direction with impart some momentum to the layer. That means, so that is the resistance to the layer. That is why I told. So this layer will form the resistance to another layer. This layer will form a resistance to another layer. That means, so the more resistance towards the bottom, because that means this is a boundary layer, this is static layer, and this is the moving layer automatically. So that is why the velocity is more on the top, and adjacent to this, this may be the resistance due to the resistance, or due to the shear stress, the tau. Maybe the gradient will be formed. So a gradient means this gradient, for example here, so the gradient means the flow velocity is very high and the velocity is literally 0 here. So that is why the fluid is coming and falling here itself. So this is the best example for the principle of fluidics, and I will explain this one in two different the experiments. Once again, you can see this video. There are there are three liquids are there, and that is poured in to the bottom chamber through a pore. The blue color one is very fast, it is like a water, so that is why it is very fast and flowing. And second one is a little density one, that maybe that is falling little slow. And the first one, the white color one, is it's like an oil, so that is why it is flowing in a very slow manner. You can see here the flow rate is very very low here, and this is medium, and this is very fast. It is flowing like water. And all the three colors depicting the fluidics. That means the flow is very fast here, and the second one is medium, and this one is very very that is the viscosity is more, that is why the fluid the flow is very very low. And this is explained in a small experiment. Just you can have a look. This the previously I told the mechanical principle of the fluidics. And just you can have a look this experiment. I will play the video. Just he is opening a tube containing a fluid, and he poured a dye on the top. You can see that maybe the center, the dye flowing very fast, and the sideways the dye flow is very very less. Actually the same one only. I will show it again. I will go to the first one. Just to have a look. He is opening it, and automatically just the center one, the flowing very fast. You can see here that means the center one, the resistance is very very less, because this side and this side the resistance will be there. That is why the two layers, the side two layers will move very slowly, but center one there is no resistance, the comparatively less resistance. That is why that is flowing in a very fast manner. So this is the best example. That means the fluid will flow in the center, not in the sideways. So that is why this will play a major role in using the maybe fermenter or bioreactor, because we are going to use that the liquid components, that's the media. So now coming to the derivation aspect, and this is not very complex, just you can understand what is there. And the examination point of view, this is very important also. The Newton's law of viscous flow states that the viscous force F, that is capital F, opposing the motion at the interface between the two layers. Just now I explained that one. The density gradient is called as dou V by dou X, and this is given by the equation. So that is F is equal to So mu A multiplied by dou V by dou X. I'll take the highlighter. The Newton's law of viscous flow states that the viscous force F opposing the motion of the interface between the two layers, the flowing with the velocity gradient. The same thing we explained here, okay, nothing is new. And the same thing is here. This F is equal to mu A multiplied by dou V by dou X. And so this one, where mu is the fluid viscosity, this is the fluid viscosity, the viscosity of the fluid, which may be considered as the resistance of the fluid to flow. And this one can be written as, okay, this equation can be written as F divided by A. By mathematics, okay, we can convert, okay, F divided by A is equal to mu into dou V by dou X. And F divided by A is a term of shear stress. That means we already had an idea, okay, that is what is the shear stress. Okay, this is the one, the shear stress is the tau, and this is the gradient is called as dou V by dou X. And you can see here this F divided by A is represented as tau. Okay, this tau is equal to the mu into dou V by dou X, but F divided by A is termed as a shear force, and it's applied the force per unit area. That means dou V by dou X is termed in the shear rate. Okay, that is gamma. Okay, so this one can be replaced by gamma, and F divided by A is replaced by tau. Okay, that means tau is equal to mu into gamma. Okay, they confirm the general relationship. Okay, the tau is equal to K and K multiplied by gamma power n. That means where K is the consistency coefficient, n is the flow behavior index or the power law index. So this may be turned into, okay, this one, because we are going to relate, okay, this the coefficient, that is consistency coefficient related with the fluid viscosity. This is fluid viscosity, and this is the consistency, okay, the consistency coefficient. And this consistency coefficient can be related with n number, that is n is the flow behavior index. So the flow behavior index, okay, pertaining only to gamma. So that is why the K multiplied by gamma power n. Okay, that is the formula. This formula you have to remember. And coming to the for a Newtonian fluid, we already explained that, okay, maybe Newtonian and non-Newtonian fluid. The first one is the Newtonian fluid. N is a 1. N is 1 means, and the consistency coefficient is a viscosity, that is a ratio of the shear stress to shear rate. Okay, so that is the plot of the shear stress against the shear rate. Okay, for a Newtonian fluid would produce a straight line. Okay, this is the model. Just you can see that. So this is gamma and this is tau. If you are plotting the values of gamma in the x-axis and the y-axis is the shear stress, so all the Newtonian fluids, the Newtonian law obeying fluids, that will form a straight line. So that is the indication here, and this is a very important property. So this is called as a rheogram. The rheogram means rheological gram. Okay, that means graph. Okay, rheogram of a Newtonian fluid. And this is the other type of fluids. For example, okay, we have different fluids, Newtonian and non-Newtonian. Other than Newtonian fluids, okay, is called a pseudoplastic, dilatant, and Casson body, Bingham plastic. Okay, all the different types are there, and this is the rheogram of the fluids of different properties. That is by plotting the value of gamma in the x-axis and tau in the y-axis. You can see here this is a straight line. Okay, that means this will form a straight line. I already explained. Okay, here the same thing is drawn here. So this one is compared with all the other. You can see here the Newtonian fluid and Bingham plastic are very similar, but the origin is the difference. But means because for the Bingham plastic, okay, this the shear stress is a little higher. Okay, that is why it is starting from the middle or in the quarter of the graph. And so, but both the direction, so that will be, okay, more okay, this will form a straight line. Okay, that means this straight line will be there. This is a straight line, and similarly for the Bingham plastic, this will be the straight line. But for the Casson body, okay, that is originating from the Bingham plastic and but curving to the bottom. And at the same time, okay, this is the origin of the pseudoplastic and the dilatant. Okay, this both are origination. Okay, is the same origin of the Newtonian fluid. At the same time, okay, that is going to the maybe it is rising and going to the bottom, and the dilatant, okay, going to the top. Okay, that is the different. So this is a very important diagram, and you should remember this diagram, okay, for the examination point of view. And note the point, okay, the origin is 0 for Newtonian fluid, and the other than 0, okay, that is the origin is the Bingham plastic. Both Bingham plastic and Newtonian fluids, okay, having the straight line. But next one is from the origin of 0, okay, that is the same origin of the Newtonian fluid. Pseudoplastic, okay, will rise and will go to the bottom, okay, that may be the slightly decreasing, okay, this the shear stress rate. Shear stress rate is also decreasing at the same time, okay, shear rate is also decreasing, but this one is slowly increasing, okay, this one, okay, not steady increase, but it is a steep increase of shear stress will be there for dilatant. And okay, the next one is Casson body. Casson body is based on the increase of shear rate, and this also increasing, but not comparable with the Bingham plastic. Bingham plastic, there is a steady line, okay, the increase will be there in the shear stress. At the same time, okay, the Casson body is not comparable with the Bingham plastic. So this is a comparison. And the coming to the different types of fluids. First, we can have the look of the Bingham plastic rheology. The Bingham plastics are similar to the Newtonian fluid. Just now I explained, okay, that one. Apart from the fact that shear rate will not increase until the threshold shear stress is exceeded. I explained, okay, the same thing, but this is a formula applied for the Bingham plastic. Tau is equal to tau 0 plus n gamma. And the n is the coefficient rigidity, and tau 0 is the yield stress. Okay, both are to be remembered, okay, for that one. And second category is pseudoplastic rheology. Pseudoplastic, it is tau is equal to the k multiplied by gamma power n. The same thing, but this is for the pseudoplastic formula. And in the case of pseudoplastic, okay, we have a property of the pseudoplastic, that is the apparent viscosity of the pseudoplastic liquid decreases with the increasing shear rate. The most polymer solutions behave as a pseudoplastic. You can see here in the graph. So this is a pseudoplastic. That means by increasing the shear rate, the shear stress is also increasing, but very slightly, but not like Newtonian fluid. Okay, there should be some proportional increase, okay, on both the shear rate and shear stress should be there, okay, for the Newtonian fluid, but in this case, okay, that is less. So that is why, okay, we have another logarithm, okay, to equate, okay, this one with Newtonian fluid, and K is the same unit as viscosity. That may be taken as apparent viscosity, and the flow behavior index is less than the unity for the pseudoplastic liquid. The smaller value of n, and the greater of the flow characteristics of liquid, okay, deviate from those of Newtonian fluid. That means this is entirely different from Newtonian fluid, and this can be represented as logarithm of tau is equal to logarithm of k plus n into logarithm of gamma. So this is the logarithm, a form of expression of the pseudoplastic rheology. And these are the examples of the different the rheological nature of fermentation broth. So coming to the fermentation, so we have to apply the physical property of the fluidics, okay, in the bioreactor. Okay, for example, if you are using an organism Penicillium chrysogenum, and the rheological type is, okay, the Bingham plastic, and the Streptomyces canamyceticus, okay, that is Bingham plastic. The Penicillium chrysogenum is a pseudoplastic, and Endomyces species is pseudoplastic. But Penicillium chrysogenum, okay, that is will behave in a different way, okay, that is the different strain of the Penicillium chrysogenum, not the same, the different strain, okay, that will behave as a Casson body also. The same organism, but it will behave in two different manners, Bingham plastic and also Casson body. You can see here the Bingham plastic and Casson body are both are different. So this is Bingham plastic and this is Casson body. So there is a deviation here. That means when compared to the shear stress steady increase, and this one, the shear stress steady increase will not be there, but it started decreasing it. So in the Casson body, the same organism will obey the rules of the rheology, but in two different cases. Xanthomonas, that will behave as a pseudoplastic also. So these are the scientists, the references worked on it, and they studied about the rheological nature of the fermentation broth of different organisms. So this one you have to remember all the organisms, and no need to remember, okay, these references also, but this one is very important, all the 6 different types of organisms. And the next type of dialant rheology is the rheological property of the fluid is dialant rheology. The apparent viscosity of dialant liquid decreases with increasing the shear rate. That's why I told that the dilatant, okay, maybe is originated from the Newtonian fluid, but the increase of shear rate, the viscosity decreases. Okay, so that is the one. Okay, so for this one, the formula is the same thing. Okay, the flow behavior index is greater than 1. It is not equal to 1 because that is more than the Newtonian fluid. The greater the value of the greater flow characteristics deviate from those of the Newtonian fluid, so that is entirely deviated from the Newtonian fluid. Thus the values of K and N may be obtained from the plot of log shear stress against the log shear rate. So fortunately, fermentation broths do not exhibit, okay, this type of behavior on behavior. An everyday example is liquid as a cement slurry, okay, that will obey, okay, dialant rheology. But anyway, we are not going to use the cement slurry type of media, okay, for fermentation process, because that is more viscous and that cannot be applicable, okay, in the fermentation process. That is why this is not in our focus. That is why not given the kinetics property and all. Next one is caisson body. So we already explained about the caisson body. This is type of non-Newtonian fluid termed as caisson body, which behaved as a pseudoplastic in that the apparent viscosity decreased with increasing shear rate but displayed a yield stress, and therefore also resembled the Bingham plastic. You can see here the Bingham plastic and the caisson body both are similar. You can see here the Bingham plastic and caisson body are both are similar because the same, it is having the same origin. Okay, because it is like same, and unfortunately, because if it is going to the by increasing the shear rate, it's slowly maybe declining. Okay, now the shear rate is not equal to the Bingham plastic, so that is why it is represented here. The caisson body rheology, that is the caisson body, and which is behaved as a pseudoplastic, and in the case of the apparent viscosity decreased with the increasing shear rate but displayed the yield stress. Okay, and therefore they resemble the Bingham plastic. The caisson body and Bingham plastic is mostly resembling. Okay, that is why it is mentioned here. And this root of tau is equal to root of tau 0 plus kc multiplied by root of tau, root of gamma. The Kc is caisson viscosity, C is represented by caisson viscosity, that is the constant, okay, we are going to apply here, and the plot of root tau against root that is a gamma will be given the straight line. So we have to use, okay, not maybe in the Rheogram, this is the Rheogram, okay, we are using the gamma here as a shear rate and tau in the y-axis. But here in the caisson body we have to use root of gamma in the x-axis and root of tau for the y-axis. So this will give the straight line. Okay, that is mentioned here, and the plot of root tau against root gamma, okay, will give a straight line, the slope of which will equal to the caisson viscosity, and the intercept of the root tau axis will equal to root tau 0. So this is the difference between the other rheological properties and the caisson body rheology, and this is explained, okay, again here. And we can go to the next topic is effect of foam and antifoams in oxygen transfer. Okay, we already completed the oxygen transfer, but this is a continuation of the rheological properties. That is why it is covered in this section. So with this maybe we cleared all the different types of rheological properties, and we can have a look. This is the first slide showing the difference between the two liquids, blue and orange one. The blue is less viscous and the orange is more viscous, and I explained the properties of the different fluids by an experiment. And this is the derivation, and this is a Rheogram, okay, by plotting the values of shear rate, that is gamma in the x-axis and tau in the y-axis. And this is a Rheogram of the fluids of different properties. So we have Newtonian and non-Newtonian. So this is only the Newtonian, and others are called as non-Newtonian. And similar to the Newtonian, okay, that is dilatant, okay, maybe that is origin and the pseudoplastic origin both are same, and the caisson body, this origin is same with the Bingham plastic. So both the Bingham plastic, which resemble Newtonian fluid, but the origin is not same. That means the shear stress for starting the origin of Newtonian fluid is 0, At the same time, okay, the shear stress is little higher for the Bingham plastic. So that is the only difference. But Bingham plastic and caisson body both are similar and having the both similar pattern, but slightly the shear stress difference will be there. And this is a dilated rheology caisson body, and everything is covered. And now coming to the effect of foam and antifoams and oxygen transfer, the high degree of aeration and agitation required in a fermentation frequently gives rise to undesirable phenomenon called as foam formation. The foam is the major threat, okay, for the production of proteins and enzymes, because the foam will denature the protein, denature the enzymes activity also. So we have to be very careful at the time of dealing with the fermentation process of production of any type of proteins or otherwise enzymes. In extreme circumstances, the foam may overflow from the fermenter via an outlet, and this will result the loss of medium. At the same time, okay, the risk of contamination. This will contaminate very easily. So that should not touch the top, the foam. If it is touching on the top, okay, maybe that will create a lot of contamination, and if it is a contamination, automatically the whole process of fermentation will be a waste one. So the presence of foam, okay, with the conventional agitated, okay, baffled fermenter may also increase the residence, the time of bubbles, and therefore result in the depleted oxygen. That means the vortex type of fermenters this is a problem, and maybe the mechanical foam control consumes, okay, considerable energy, and it is not completely reliable. So there are previously, okay, the mechanical foam controlling machines are there, so that will rotate on the top, or otherwise the foam may be collected from the fermenter vessel, and that may be ground by a blade or something. It is like the mixer blade or otherwise a homogenizer, and again after removal of the foam, again that is going to be poured into the fermenter vessel. So this will create a lot of complications. Sometimes, okay, this may create the contamination also. The chemical antifoams when compared to this may be better when compared to the mechanical foam control, because mechanical foam control is time consuming. At the same time, okay, that may create a lot of complications related to the contamination. So all the antifoams are maybe the chemical antifoams are surfactants. Surfactant means that will reduce the surface tension and be expected to have some effect on oxygen transfer. Surely 100%, okay, that will affect the oxygen transfer, but we have to be very careful. That should be very negligent, okay, because it should not the involve in the antifoam should not interfere with oxygen mass transfer. Okay, so that we have to take into consideration, and we have to select a particular type of antifoaming agents, okay, in the particular type of fermentation process. The antifoam may accumulate at the gas-liquid interface, resulting in an increase in the resistance of oxygen diffusion. For example, if there is a bubble, means the bubble layer, the interface between the liquid and the air, okay, may be there, and in the interface, all the antifoam agents, okay, will be maybe coated. So that will be disturbing all the oxygen diffusion into the media. So that may be the big problem, okay, in the antifoam agents. And this foaming increases gas holdup, okay, in the vessel, that in turn, okay, increase the broth volume and influence the liquid height in the fermenter at which it is practical to operate. And if inadequate space is provided, okay, above liquid level for the foam control, then the copious amount of antifoam must be used to prevent the loss of broth from the vessel. That means maybe, for example, okay, if we have the total volume of the fermenter vessel, okay, that is 1 liter, for example, and you should not use the media for 1 liter. You can operate, okay, only 700 ml. That means only 70% of the total volume you can use it. If your the vessel size is 1 liter, you can use 700 ml. The remaining 300 ml, okay, will be given for the foaming. You have to anticipate that, okay, the foam can be formed, and you have to control the foam. And if you are using the liquid, okay, till 900 ml or 950 ml, so there is no space to breathe. So the sparger has to give the air bubbles, and the air bubbles should reach the top. At the same time, okay, some foaming may be formed, okay, in all the fermentation process. So we have to leave the space for the foam. So that is why the 30% of the fermenter vessel should be given for the foam settlement, and the foam can be easily controllable by using anti-foaming agents. So above a critical liquid height, the the KLa values, the decreases dramatically, due to the excessive use of antifoams. So this KLa value will automatically decrease in all the cases of antifoaming work, but you have to adjust it. For example, if you have the mass flow controller, automatically that will switch over the increase of speed of the rotor. At the same time, that will increase the flow of oxygen also. That will manage to control the dissolved oxygen level within the vessel, in spite of adding the antifoam agents. But if you are using the manual one, without a mass flow controller, not an automatic fermenter, what will happen? So automatically this by the addition of the few drops of antifoam agents, these antifoam agents maybe the covering the liquid surface or liquid interface of the air bubble, and automatically disturbs the KLa value. This KLa value is decreasing. That means the mass transfer, that is oxygen mass transfer, may be disturbed here. That is why the dissolved oxygen level may be going to be decreased. So ultimately leads to the poor multiplication of the microorganisms and the poor yield. So many things will happen. So that is why preferably you have to go with the mass flow controller, and without the mass flow controller there is no use at all. So with this we can conclude the effect of foam and antifoam on oxygen transfer, and scaling up and scaling down is the next topic. And so in this we can have a look of what is the scaling up method and what is the scale down method, and we can go with one by one. The first one is scale up. Scale up means to increase the volume. From the, for example, if you are using with the pilot scale fermentation process, that is 30 liters, and you want to increase to 300 liters or 1000 liters, that is called a scaling up. So the increase in the scale, that is the volume of your fermentation vessel and the volume of your media from minimum to maximum, that is called as scaling up. Scaling up or scale up means increase in the scale of the fermentation process. For example, from the laboratory scale to pilot scale, and you can use it. In our college, we have 1.75 liter fermenter, is a bioreactor, and the total working volume is 1.5 liter, and that 1.5 liter, it comes under laboratory scale fermentation process. And if you want to go for the pilot scale, that is 10 liter to 300 liters, you can use a pilot scale fermenter, and that pilot scale fermenter is a next level, that is scale up method. Increase in scale means increase in volume. The volume is going to be increased and the problems of the process scale up are due to the different ways in which the process parameters are affected by the size and unit, because it is not the power you are going to apply the same. For example, if you have 1.75 liter fermenter and you have 1000 liter fermenter, so whether the power given for rotor is same and the power given for 1000 liters fermenter is same, entirely different, because including the size of the motor is different, and liquid handling, the machineries are different, and the probes are different. So entirely different. The setup and the designing of the fermenter, everything is different, but each and every parameter will be considered in this case. But it is a task of the fermentation technologist. Usually the fermentation technologies to increase the scale of the fermentation without the decrease of yield. So we should not compromise in the case of yield. You can increase the size, at the same time the yield should be maintained or otherwise increased. If the yield reduction occurs, to identify the factor which gives rise to the decrease and to rectify it. If you have the problem of decrease of yield, then you have to work it out. What is the parameter is interfering, and that has to be rectified. That is given here. And the major factors involved in the scale up are number one is inoculum development. We can see one by one. The first one is inoculum development. The inoculum development, for example, usually I told in the previous lectures, the inoculum preparation is it's play a major role. Inoculum preparation is approximately 1% to 3% and sometimes 10% also. But 10% is very rarely used. 1 to 3% is very commonly used. For example, if you have approximately 1 liter fermenter, so you need minimum 100 ml. That is 1%. The 100 ml is the minimum volume for the inoculum development. You can do the 100 ml the inoculum by easily maybe by overnight the seed culture preparation and overnight culture. You can use it. But at the same time, 1000 liter fermenter, if you are scaling up the same thing, 1000 liter 1 liter to 1000 liter fermenter, what will happen? So the 10 liter of the inoculum is required. So for preparation of 10 liters of inoculum, you need a mini the fermenter. The total size is the 12 liter fermenter, and the working volume is 10 liter. So you need a small fermenter is required to prepare the inoculum. So that is the additional investment for you. If you want to increase the volume of fermentation from 1 liter to 1000 liters, in between you need another fermenter for the preparation of inoculum. So that is the cost effective, and cost investment is also there. And an increase in the scale may mean that extra stages must be incorporated into the inoculum development program. The extra stages, a word is a simple word, but there's a big story behind this. That means I told just now, the 1 liter is a fermenter, and if you want to scale up to 1000 liter means you need minimum 12 liter fermenter. That is the extra stage is required, as well as the design of the inoculum train and stability of the strain must be assessed to ensure that it can retain the productivity for the increased number of generations required. For example, you have to check it that maybe the completely the strain stability and maybe the contamination, the factors, all the factors you have to check it. The strain stability is very important. You should not subculture from the mother culture on all the ways, and you should not subculture continuously from the subculture to subculture means automatically, so that will decrease the productivity. So you should have the seed culture or mother culture. From that you have to take the strain for the inoculum preparation, if it is 10 liter also, if it is 1 liter also. So that is very important. And the second parameter, sterilization. The sterilization is a scale dependent factor. If you are having 1 liter fermenter, the sterilization is very easy because you can keep the whole fermenter or bioreactor into the autoclave and you can sterilize it. But if it is 1000 liter, just you can see that the huge volume, the 1000 liter means that the huge volume, the huge machine has to be sterilized by steam sterilization only. That is the in situ sterilization, because we cannot keep the whole the 1000 liter fermenter within the autoclave. So there is no autoclave, the big autoclave like that. So what we can do, we can pass the stream into the steam into that the vessel, and we can increase the temperature to 100 degrees C to kill all the organisms in a long duration. So this is called as sterilization. This may be the problem. And the environmental parameters like nutrient availability, we have to look into that. And the pH, that is a big task, maintaining the pH. And temperature, that is also the big task, because in 1 liter of the fermenter you can maintain the temperature by using any water jacket, heat water jacket or something. Direct filament is also you can use it, but at the same time 1000 liter fermenter and all, and you have to use big heating elements outside, and you have to heat the jacket also, and a very sensitive thermostat is required to control the temperature. Next one is the DO probe, that is oxygen transfer rate and dissolved oxygen concentration. This analysis. So we need a big maybe the sensor, the DO sensor, for the continuous monitoring of the DO level. And shear condition, that means how much the shear rate is there. That shear sensor is also required. And dissolved carbon dioxide concentration, carbon dioxide removal rate is also required. That is, we need another probe. That is carbon dioxide probe is required. And foam protection. The foam protection is a bigger problem in the big reactors, and we have to use anti-foam agents on the top. And this one we have to take it very carefully, because the foam protection is very common problem in the big fermenters. And increased heterogeneity, that you have to check it. Homogeneity is accepted, but heterogeneity means this each and every time the productivity or the recovery rate and yield and the product the yield rate may differ. So you have to standardize it, and each and every time, and you should get the particular product yield with maximum or minimum. This the deviation, the standard deviation, maybe the plus or minus 1 or 2. That's all. And all the mentioned the parameters are affected by agitation and aeration. That is also a big problem. Agitation is by using the impellers that will agitate, that you have to use the bigger motors for 1000 liter. And aeration also, you have to use bigger compressor to pass the air into the sparger. And either in the terms of bulk mixing is required, and points A, B, C, D to H all are related to the bulk mixing, while D, E, F and G are related to the airflow, agitation and oxygen transfer. For example, D, E, F and G. So D, E, F and G, okay, all the four related to the oxygen transfer, because this will impact on oxygen transfer, because carbon dioxide will impact on oxygen mass transfer. Shear condition is also involved in the oxygen transfer, and this is the detection of oxygen, because you have to use a sensor that should be more sensitive, and the foam production that should be controlled. If more foam means automatically oxygen diffusion rate may be decreased. You should always be remembered that the inoculum development and sterilization difficulties may be the reason for decrease in the yield when the process is scaled up. Okay, the yield may be decreased. That is a bigger problem if you are increasing. Okay, there is a scaling up. Okay, and you have to correct the agitation and aeration problem, and better you can use the mass flow controller to tackle these issues and all. Next, coming to the scale down. Scale down is very rare, and maybe if you want to decrease the scaling down, okay, these are the points, okay, you have to consider. Analyzing the industrial fermenter to be used in a new process or a vessel being used in the existing one. So mimicking the large scale conditions in the lab scale system also. You have to mimic the same condition, okay, of a lab scale condition, okay, in the large scale condition in the lab scale. That is, if you have 1000 liters, you have to use maybe the same type of environment, okay, for the lab scale system. The optimize the conditions or resolving the bottlenecks in the scaling down system. The optimizing the condition means if you are scaling down, you have the problem is maybe the minimizing the power of the motor, and also the controlling parameters like the minimizing the compressor size and everything. Just you have to look into that. That is the bottleneck that may be the problem, and this may be easily tackled down when compared to the scaling up. The scaling down is a little easy when compared to scaling up, because you are going to minimize expenditure, you are going to minimize the infrastructure, if you are going to minimize the complexity of the machines and everything. And translating the findings back to the industrial fermenter, you have to correlate with the factors responsible for large scale fermentation process, and also you have to compare with the lab scale fermenter also. That is why you should always compare, but the yield should be maintained, and implementing the improvement on the large scale. And you can use the implementation of the same thing, okay, in the large scale. You can compare both, and you can run parallelly also. Sometimes, okay, in the industries, okay, they will do the large scale, and they will do some the miniature pilot scale also, the mini scale, that is a scale down process, to analyze, okay, what are the factors are going to be involved, and what are the risk factors, and what are the problems going to be occurred. So that is a pilot study or pilot scale of production, and based on that, okay, they will apply the problems and overcome the problems, and they will do the alternate methods, okay, in the large scale. The aspects of scale down that are simplest to address are the medium design. So you have to apply on the medium design and medium preparation and sterilization. So when compared to scale up, okay, these all very few parameters are there, and the inoculation procedure is very simple when compared to the large scale to lower scale. And number of generations, the industrial scale fermentation requires a greater number of generations than does a laboratory one. Because I just now I said because for 1000 liters, if you have, means you need the different generation. That means the inoculum is you need in between and another one, okay, for the inoculum preparation, the fermenter, and so that is require, okay, more generation. That is not the same generation you are going to use it. So that is the industrial scale fermentation requires a greater number of generations when compared to the laboratory one. You can, for example, you can take a mother culture and you can use it in the maybe 100 ml of the conical flask, and you can use it directly for the 1 liter fermenter, but it is not the same for a 1000 liter fermenter. So the 100 ml has to be poured into 1 liter, and 1 liter from that maybe you have to pour into the 12 liter fermenter, and to start the inoculation process. So the inoculum preparation, maybe it will increase the generations of the microorganisms. The number of generations may be increased. So that is the point discussed here. So with this, I think we concluded all the aspects of scale up and scale down. And next, coming to the fermentation economics, I think, okay, this is the last chapter, okay, in the upstream. in the upstream, okay, the fermentation economics is a very, very important point, and maybe this is not covered in industrial microbiology syllabus, but this is for the biotechnology students, and including the other students, other department students also, they can know that, okay, what is the factor behind this. For example, if you want to start an organization or otherwise a biotech startup to produce any enzyme or otherwise any the bioproduct, okay, with the help of fermenter, so this economics part, okay, will play a major role. The fermentation economics is a major role, and we can see a lot of factors involved here. So this is a purely economics parameter related to the fermentation process. If a fermentation process is to yield a product, so ultimately your aim is to produce a product, to yield a product at a competitive price, and you should not produce, for example, we have the human insulin available at all the medical shops, and the cost of the human insulin is approximately 200 to 300 rupees. So based on the quality and based on the make, if it is maybe the multinational company, okay, that may be more very higher rate. At the same time, okay, if it is local make like Biocon, the cost of the production is less, so that is why the cost of the product is also less. So that is why the competitive price means, okay, if you are producing a product with a higher rate, you are spending much for the production. At the same time, you have to put all the expenditure, okay, to the product. So that is why the price may be increased. That is why you have to choose a different method to reduce the cost. The chosen microorganism or animal cell culture should give the desired end product in predictable. So that is very important. You have to predict it. Okay, what is the cost and what is the yield and everything, and economically adequate. So that economics aspect, that should be adequate and viable, controllable, handleable, and including the quantities of output, that is the yield also, you have to predict it. And several basic objectives are commonly used in the development of the successful processes, so which will be economically viable. The first one is the capital investment. For example, if you are starting a biotech startup, and if you are starting a production of any product using the fermentation technology or industrial microbiology or bioprocess technology, whatever may be, the capital investment will play a major role. That is, a capital investment in the fermenter and ancillary equipment should be confined to the minimum. So what you are going to produce it. So I'm going to produce, okay, maybe a particular quantity. For that I need only the 100 liter fermenter, means that is more than enough. So no need to put lot of money for purchasing 1000 liter fermenter. If you want only 100 liter, that is, if it is solving your purpose, means, okay, that is more than enough. Just you can do with 100 liter fermenter. And if you are going for the higher level, maybe if the company goes to the next level, okay, maybe this is a corporate company and also the increasing the production, and if your marketing strategy is entirely different, and if you are expanding your horizons, and if you are selling your products to other countries also, and you have to produce much more, means then you can scale up. So unnecessarily, okay, maybe the capital investment for the fermenter and ancillary equipment should be avoided, okay, here. That is why it should be confined, okay, to a minimum level, and providing that the equipment is reliable and may be used in the range of fermentation process. So what is the meaning of reliable? So for example, in CMS college, okay, we had an equipment, okay, that is a B-Braun Sartorius. So now that is taken by Sartorius and B-Braun Biotech, okay, that is the name of the company of that one. The B-Braun is a very big company. That is the company origin is Germany, and we analyzed, okay, all the bioreactors, and finally we concluded with selected B-Braun, because B-Braun is a reliable one and very maybe very reliable, and it will give the reproducible results also. So there is no hassles, okay, in operating the fermenter or bioreactor. At the same time, okay, in locally, okay, we have so many companies out there. If I am focusing about only the money, I can think about the local companies also, because the cost may be only 10%, not 100% of the total investment. So the 10% is very small amount. At the same time, if I am purchasing a product, that product may be last long, okay, maybe for 10 years, okay, nothing will happen, including we bought, okay, in the year 2003, okay, still it is running. If it is maybe local product, maybe the ingredients and also the machines and the motor and everything is maybe low quality, means, and you will get lot of complications for each and every run. So that is why you have to be very careful about the reliability of the equipment, and you have to do a project, and maybe you can analyze it, and based on the survey you can get it. So maybe if you want to put some little extra, 10% or 20% or 30% extra, okay, for the capital investment for the reliable product, I don't think, okay, that is a waste. Okay, that is an investment actually. And the raw material should be very cheap and as possible, and utilized frequently and efficiently. And the raw material, you should not put it for, okay, much cost. A search for the possible alternative materials might be made even when a process is operational. Okay, that means, okay, the raw material, if you are getting the product, the raw material, for example, okay, the media components and media agents, okay, all the agents, okay, if you are putting, okay, much more money, okay, for the media preparation, that will increase the cost of your product. So that is why you have to be very careful in that case. And the third point is highest yielding strain. The origin is, so your starting material is your organisms. Okay, that means if you have a very good organism, and that organism is good, means, okay, it is not like we should not use the term good, it is highest yielding strain. Highest yielding means that should yield a maximum of your product of interest, that has to yield more. Okay, and based on that, first of all, you can focus more research on identifying the particular microorganism, and if you confined with the microorganism, then you can preserve it as a mother culture. You should not disturb it, and they should not maybe disturbed or contaminated, and keep it as a lyophilized culture, or otherwise, okay, in multiple copies, and also you can keep it very safely in -86-degree freezer. And any time, okay, for the starting of the fermentation process, your culture should be there, the mother culture, and don't subculture frequently, okay, that mother culture, automatically that will lose its characteristics. And the highest yielding strain of the microorganism or the animal cell culture, if you are working on any protein production or otherwise growth hormone production, the animal cell culture is required, or monoclonal antibody, the animal cell culture is required. So in that case, okay, you have to choose the same thing, that is highest yielding strain. That means the particular cell line, animal cell line, okay, to be chosen very carefully. And there should be a saving in labor, okay, whenever is possible, because and automation should be used, okay, wherever it is possible and feasible. Okay, so the labor cost, okay, may be more, okay, you have to pay much for labor, because if it is an industry, the operating the instrument, and maybe the preparation of media, and maybe the routine maintenance of the instrument, that is why the cost of the labor is more. But nowadays, okay, this the most of the labors are reduced by the companies, because they went for automation. You can control all the processes. You can see everything on online mode, and in the control room, it is like a, okay, rocket launching station. Okay, just you saw in all the movies and all. You know that, okay, the SpaceX program. All the scientists, okay, they may be sitting in a room with in front of the monitors, and they are controlling all the activities of the rocket. So similarly, okay, here you are going to do the fermentation process, and all the fermentation process may be controlled in the controlled room, that is operation room. Okay, that operation room, okay, with all the softwares, and that will control each and every parameter of the bioreactor, including we have a machine, that is the bioreactor Bebron, and that is fully loaded with all the control parameters. Each and everything is controlled. All the control parameters may be controlled from the software. Okay, that is Bebron software, and that is connected with the internet, and you can control the whole equipment from any part of the world. Because if it is controlled with static IP, you can control the whole parameter. Just you have to load the media, and you have to inoculate it. After inoculation, and you have to fill all the acid, alkali, and antifoam agents. That's all. And you have to keep, okay, this compressor with gas. So everything is perfectly controlled by the machine. So there is no manpower is required. So similarly, so you can try to avoid save the labor, okay, in the fermentation. Okay, that will maybe give a better economically viable product. And the fifth point is the growth cycle, okay, should be as short as possible. The growth cycle means maybe if you are producing an enzyme, means, okay, within 3 days, if you are getting an enzyme, the total yield means that is better. At the same time, okay, if you are going for 5 days, means the extra 2 days means that is 2 days extra production cost. That will increase your product cost also. Okay, and some of the products like antibiotics, usually the antibiotics produced in the late of that is end of stationary phase, or starting of the death phase. In that case, okay, you have to run the fermenter or bioreactor nearly for 21 days or 22 days. Just imagine, okay, how much will be the production cost. So that will be more. That is why mostly all the antibiotics are little costlier when compared to other products like citric acid, lactic acid and all. Okay, when compared to the primary metabolites, and the secondary metabolites are much more costlier because it will be produced only in the later stages, and the production cost is much more higher when compared to the primary metabolites. The recovery and the purification procedure should be as simple as possible, and maybe if it is really needed, you can go for the downstream processing, and maybe if your application is directly for extra, maybe a superficial application. For example, if you are producing a detergent enzyme, for example lipase enzyme or amylase enzyme or otherwise a protease enzyme, to be applied as a detergent means, okay, no need to purify, just you can apply ammonium sulfate precipitation just to precipitate the the supernatant, okay, and maybe again maybe you can dissolve, okay, the precipitate and reconstitute the precipitate in the buffer, and maybe filter it, and maybe you can use that liquid, okay, that one, okay, after dialysis. So this is the as much the cost may be reduced, okay, in that case. Recovery and purification, if it is really needed, you can go for the purification, or otherwise you can go with ammonium sulfate precipitation, and you can stop it and do the dialysis, the mass dialysis, and prepare the product and powder the product and pack it and sell it. That's all. So unnecessarily don't spend much more money, okay, for the downstream processing. If you are entering into the next segment is downstream processing. So that is a huge investment segment. That means you need a lot of manpower and highly technical manpower. So it is not a person needed for operating the fermenter is different. A person working on the downstream processing, that like operating the chromatography chambers and the chromatography, okay, this the columns and all, HPLC, FPLC, and all the maybe equipments are more sophisticated when compared to the fermenter. So that is why you have to invest more for the manpower, much more when compared to the manpower of the upstream. Okay, and so this point is very, very important. Recovery and the purification procedures should be as simple as and rapid as possible, and you should not keep much more time, okay, for purification. And the seventh point is the effluent discharge, okay, should be kept at the minimum, because your factory and also your product, okay, should not disturb the environment. Okay, the effluent discharge should be very minimal, and that should not disturb the ecology of the whole area, and you should not spoil the environment. The heat and power should be used efficiently and maximum possible. Okay, you can have the alternate power supply, because in India, okay, we are reliable power supply is required. You should have always the alternative power supply, and 24/7 power supply is required. And it is not for waiting, okay, 1 hour, 2 hours to resume the power. It is not like that. The fermenter and everything will be clogged, including the sparger, okay, that may deposit, all the pores will be deposited, okay, with the microorganisms, and the sparger will be clogged. The heat and power should be used efficiently. The space requirements, you have to use the space as minimum as possible, okay, because you have to keep that one in the sterile condition. But there should be some the allowance for the potential expansion in the production capacity, and you have to think about, okay, the next level also. If you are running a small equipment or a small industry, and if you have the scale up option, and think about the expansion facility also, and you should not change the place, or otherwise you should not frequently changing the places. That will disturb, okay, your the production efficiency, and also the production maybe the quality and all. And all the above must comply with the safety guidelines and regulations of the biosafety, and that is very, very important. So these are the points we have to keep in mind, okay, in economics, that is the fermentation economics. So this is a very important point, okay. That is the end of upstream processing, and maybe these are the points also very important, and this already discussed, okay, in the media preparation and all. So again, I'm telling, okay, these points again with some examples also. Isolation of microorganism of potential industrial interest. For example, the important factors, okay, which will be economical significance that might be selected in a well-planned screen, okay, could include the growth on simple cheap medium. Just now I told, okay, the media should be very cheaper, Okay, the growth at a higher temperature, okay, that should be maybe you can reduce the cooling cost. Cooling cost is higher than compared to heating cost, and the better resistance for contamination, strain improvement, and the third one is market potential, and fourth one is the plant and equipment cost, the cost of the plant and the cost of operation that should be compensated, and fifth one is the media cost of the media, and the air sterilization is also there, that will cost much, and you can use some of the parameters like PTFE filters, okay, for sterilization as a local level. And heating and cooling, preferably you can use the heating method instead of cooling, and if really the cooling is required, maybe you can use some the natural cooling methods instead of making the refrigeration or otherwise the cost consuming cooling methods and all. The fermentation method, just you can do it in the normal temperature, that is okay, but in the very cold condition, that may increase the cost. Okay, and aeration and agitation also. So this aeration and agitation, this just you can use the normal level, but more aerated thing is better. But if you are using anaerobic cultivation, that is very difficult, and maybe is handling the anaerobic condition is also very difficult, and you have to use a nitrogen gas or otherwise sulfur gas also, so that is more toxic also, maybe if any leak or something is there. And we have to be very careful with the aeration and agitation part. And agitation, sometimes the motor may be heating up, and maybe the rotor or the moving parts may be heated up. Just you have to sense what is the heat, and if anything is required, any lubrication or something is required, just you have to apply it. The fermentation which are anaerobic, where oxygen is undesirable, okay, that is the first point. Second one is fermentation which are minimal oxygen demand, okay, that is ethanol like one, okay, maybe the minimal oxygen is supplied, that is more than enough. And high oxygen demand for antibiotics, that is primary metabolite and secondary metabolite production, okay, this will produce much more aeration agitation cost also. And batch process and cycling times. In a batch process, the productivity must be determined for the complete process cycle. Here the productivity is defined as grams per product, grams of the product in decimeter cube, okay, per hour. And this productivity is based on the combination of the time and actual fermentation, and the time to prepare the fermenter ready for the next run. Okay, if you are doing the fermentation process and actual fermentation, and after that how much time is required to clean up the process, the fermenter, and keep it ready for the next fermentation process. And if it is much, maybe the gap will be there, means that may be a more disturbing factor, and your productivity may be disturbed. And the continuous cultures may be for the bulk cultivation, and maybe the continuous production in the industry level, okay, this may be advisable. So this is mainly to produce microbial biomass and the enzymes, okay, the glucose isomerase enzyme, and the milk industry, especially the buttermilk production and yogurt production. So this continuous culture, okay, may be very useful because the running cost is very less when compared to the batch and fed batch. And recovery cost, the recovery cost means that is for the downstream processing. You should spend minimal cost for the downstream processing. At the same time, if it is really needed, you have to go for the purification cost, okay, till the better purification product. For example, two things you are going to produce it. One is the enzyme for the detergent. Another one is human insulin. Okay, that is a human insulin that is from the recombinant protein. So the first one is you are going to apply the powder or the protein powder or the enzyme powder in the detergent, mixing with the detergent, and that is not taken by the human, okay, orally or otherwise intravenously. But the second one is you can see that, okay, there's the human insulin. That human insulin is the intradermal or the intramuscular injection, okay, maybe there. Usually the intradermal part. Okay, so in that case, that is going directly into the body. That means in that case you have to purify the product, okay, till its homogeneity. Okay, that means, okay, 98% homogeneity is expected. In that case, you have to do the purification. That purification, that is a lot of stages will be there. Ion exchange chromatography and gel filtration chromatography and affinity chromatography may be there, and maybe the different types or combination of one or two type or multiple types of chromatography is required, and you have to spend much more time, okay, for much more cost is involved for the recovery. And after usage and recycling, and after usage, just now I told, okay, this may be the many fermentations have higher daily water usage, charges of water increase that may be there, and many of these processes will become vulnerable, okay, to cost escalation because of the relatively large volumes of water requirement per unit volume of the product. The water requirement is more because to cool the fermenter and to handle the fermenter and to wash the fermenter, so huge amount of water is required. So this is also the major problem, okay, that is the water requirement, and recycling also may be major problem. Effluent treatment, that is the responsibility of each and every factory, so they have to recycle it, and so only the recycled product, recycled waste only may be exposed to the environment, and they have to check what is the solid loading, the pH variation, the nutrient level, the temperature, the fluctuation, everything they have to check as per the government norms, and the follow-up of the environment factors, that is the completely maybe to be considered in a very strict manner. So with this, I'll conclude okay, the first segment of the bioprocess or fermentation technology or industrial microbiology. So upstream processing is over, and we have the next topic, downstream processing, and we can have it one by one later. And with this, I'll stop my presentation. I hope you enjoyed, okay, this session, and this is very important, okay, not only for the studying and examination point of view. You will get a lot of knowledge, and this may be applied, okay, in the industry also, if you are going and joining as an industrial person, and if you are starting up your own startup, this may be very useful. All the very best. Thank you.